Today we're going to look at higher derivatives. So what do you think this thing here means? Well, what it actually means is that we can differentiate once, and I know I've got v and t here, but it's the same idea as when I've got x and y. First of all, I need to write it in terms of powers. And then I can differentiate it. Now, if I want to find this thing here, we call it d2v by dt squared. I think I'm going to write that down. d2v by dt squared. It's a bit of a strange way of saying it, to be fair, but you don't tend to say d squared v, you'd say d2v by dt squared. Don't know, that's how we do it. And what it means is that we differentiate a second time. So it's actually d by dt of dv by dt. And as I sort of indicate up here, this is how this notation comes about, because you can see I've got two lots of d and one lot of v, so it's d2v, and then I've got dt times dt, so it's kind of like dt squared. This is only loose, really, because you might argue, why don't I put a squared here? Yeah, okay, I'm only giving you a rough motivation. There are other reasons why the notation is as it is. We just need to remember this and be able to apply it. So in this case, the second derivative would be 30t minus 2t to the minus 3. And we could keep going. We could find the third derivative. What do you think that would be? It would be, well, I'm not actually interested in what the function is particularly, but it would be d3v by dt cubed, and so on. And you could just keep differentiating as much as you want. And actually, why not? Let's give it a go. Here is a function for y. Okay, what I want you to do is to find as many higher derivatives as you can. Go for it. Okay, the absolutely essential thing again is writing it in powers, x to the power of something. So we get x to the half, and we get x to the minus 1. Okay, bring the 4 down, reduce the power. Bring the 2 down, that cancels out, reduce the power. The 6 disappears. Minus 1 from the half. This should be quite quick at this point. We've been practicing this a lot. If not, go back and practice. The minus 1 comes down, so it becomes plus 1. Okay, very easy to make little mistakes, but it's practice, practice, practice. Okay, let's keep going. As you can see, when you've got sort of an integer, oh no, sorry, a whole number, like a positive integer, then eventually it's going to disappear because the power just keeps decreasing until you get to your constant and it goes. Whereas when you've got these fractional indices and negatives, actually it just gets more and more negative. Okay, I think that's okay. Right, let's do one more. Sorry, that should be a 4. You can actually see this one sort of alternating. this term between negative and positive because of the negative power. And the same for this one. Okay, this is good practice of just making sure you can take fractions and -1 from them quite quickly. I think I've illustrated the point though, so we can find the first. This is called the. I didn't say this actually, did I? This is called the first derivative. Before we've just called it the derivative, but now there's going to be more of them. Then this is the second, third, fourth, and so on. Okay, now you might be thinking right now, why on earth would you want to differentiate 4 times? And aside from just because we can, there is a physical reason. And I'm going to illustrate it to you. So, the displacement is a bit like the distance in physics, but actually distance is always a positive number, whereas displacement can be negative. It's how far you are away from something. Now let's call it x. Now, if I find dx by dt, what I am finding is the rate of change of displacement with respect to time. I mean t to be time here. I'll just put that over here. The rate of change of displacement with respect to time. Now that, in fact, is the velocity. So finding the first derivative has a physical meaning. Okay, what if we find the second derivative? Which, by the way, is the first derivative of the velocity. They're the same thing. This is the second derivative of the displacement with respect to time, but it is actually the first derivative of the velocity with respect to time, i.e. how is the velocity changing with respect to time? And the answer is, it's the acceleration. So the second derivative has, in many cases, a physical meaning. And we can go on actually. We could actually find out the third derivative of the displacement with respect to time, which would be the second derivative of the velocity with respect to time, which would be the first derivative of the acceleration with respect to time. And this actually has a special name called the jerk. Okay, I'm not making this up. It is the rate of change of the acceleration. Now, in fact, useful on roller coasters, because when you're on a roller coaster, it's not just about how quickly you're accelerating, it's about how that not just like a constant acceleration, but it's how the acceleration itself is changing, and that affects you on the ride. So you do feel this quantity. We can actually keep going. And the next one is called the jounce or the snap. This would be the fourth derivative. We start losing meaning at this point, really. The rate of change of the acceleration. Not really sure what that is, but it does have this name, and I'm sure it is used in some capacity. Actually, I think some physicists thought it'd be funny, and they carried on, and they found the fifth derivative, which they called. I don't think I'm making this up. I think this is on Wikipedia. The fifth derivative was called crackle, and the sixth derivative was called pop. If you are familiar with a certain English, or should I say British, breakfast cereal, then you may understand their sense of humour. But what I would say, okay, if take anything out of this, is actually you'll see this later on in mechanics, this link between displacement, velocity, and acceleration. And be aware that actually finding these higher derivatives can be useful, as well as just doing it just because we can. Now, yeah, we don't tend to get many more higher derivatives, but actually you can, in many cases in physics, you can write down mathematical equations in terms of derivatives, and it typically won't go any higher than 4, but writing these things down can be incredibly useful for solving problems. Okay, let's see how higher derivatives are useful. And actually, we're going to look at the second derivative and how it's useful with respect to stationary points. Previously, we found that stationary points were when dy by dx were equal to 0. And we could work out either whether they were maximum, minimums, or some other points of inflection using that. However, we could not say which they were. We didn't know whether it was a maximum or a minimum, we just knew it was a stationary point. The second derivative allows us to do that. So if I focus on this one here, if dy by dx is equal to 0 and d2y by dx squared is greater than 0 at the point, at the stationary point, I'm going to call it SP for short, then we get a minimum, which is a bit counterintuitive because it's like positive and we get a minimum, and it's negative and we get a maximum. But let's have a look at why that is. So here I've got a curve going down and back up. I get a minimum at P. If you look at the gradient just to the left, like draw a tangent, that wasn't a very good tangent, draw a tangent, then it's negative. Then it becomes, the gradient of the tangent is negative. Then the gradient is equal to 0, and then the gradient of the tangent is positive. You can see it's going from negative to positive. It's actually increasing. That's why it's greater than 0, because the gradient, remember that's what dy by dx squared is. It's the gradient of the gradient, and the gradient itself is increasing. So the gradient of the gradient is greater than 0. Okay, the main thing is you just need to know this. This is a fact. And similarly, if you have a maximum, then you get a positive gradient, then a 0 gradient, then a negative gradient. It's going from positive to negative. It's decreasing. The gradient of the gradient is going to be less than 0. So these are facts that you can have, and you can then classify stationary points. There's one scenario which is just a little bit more difficult, and that's if the second derivative is 0 at the stationary point. Then we don't know. We can't say for sure whether it's a maximum, minimum, or a point of inflection. We need another method. We'll look at this in a second. So these are the types of stationary points. Okay, we can get a maximum, minimum, point of inflection. We could get a point of inflection going the other way as well if it comes back down like that. So just be aware. And we'll talk more about that in a minute. At the moment, let's just focus on the fact that we can use the second derivative to find this and this. So a little quick test, I'm going to hide that. Right, what happens if the second derivative at the point is less than 0? Okay, that's when we get a maximum. What happens when it's greater than 0? Minimum. What happens when it's equal to 0? Sad face. Okay, let's do an example. So this just links into last lesson where we were able to find stationary points, or turning points as they're called here for graphs, but now we're going to classify them. So I want you to pause the video and find the stationary points. There'll be more than one because of the way this question is phrased. And if you're feeling confident, you could give it a shot at classifying them. Otherwise, you could look through my example on it. Okay, first things first, actually, we need to write it as x squared plus x to the minus 2. So it's all x to the power of something. Then we find the first derivative, which is this. Okay, and then say that it's equal to 0 at the turning points. Now we've got an awkward equation to solve. It's not that awkward. Okay, first things first, I'm going to write it back using index notation. And then it's up to you what you do at this point. I'm going to multiply through by x cubed. I always think it's just a good shout to get rid of these things. So multiply through by x cubed, we're going to get 2x to the 4 minus 2 is equal to 0. I've just got to remember that x can't equal 0 if I'm being technically proper mathematically. I should, because maybe although there isn't a solution, sometimes you might multiply through and you might get a solution that you're not meant to get. Okay, then I think I'll add 2 to both sides, divide through by 2, and we get x to the 4 equals 1. This technically still holds throughout. Okay, I can take the 4th root of 1, and we're only dealing with real numbers here, so there are 2 answers, plus and minus 1. When x equals 1, I need to find the value of y now, because it's the turning point, so just put 1 into here. 1 squared plus 1 over 1 squared, that's just going to equal 2. So I get 1, 2 as my first turning point. When x is equal to minus 1, it's actually the same thing. Y is equal to 2 again. Okay, let's see what happens now. So this is the crucial bit. I need to do the second derivative, because I need to classify these. So d2y by dx squared, I need to differentiate this thing again. It's going to be 2 plus 6x to the minus 3, 4. Which is 2 plus 6 over x to the 4. When x equals 1, so this is the crucial bit now, I substitute my stationary point in to the second derivative. Okay, and it's going to equal, it's actually going to equal 8, because it's going to be 2 plus 6 over 1. So I get that 1, 2, and this is greater than 0, and this is going to be a minimum for the reasons discussed above. When x equals minus 1. Okay, well, you might have thought I'd give you a maximum here, but actually I've not. That's not what's happened. We actually get 8 again, and we get a second minimum. So I think the moral of the story here is don't always expect to get 1 as a maximum, 1 as a minimum. Could well happen, and there are times when it will, for sure. If I look at a cubic, for example, it looks like this. I will get a max and a min if I get at least one of them. Obviously, some cubics look like this, and you don't get either. But if you get a maximum, the other one will be a minimum. This is a more complicated curve, and it doesn't actually give you a local. Remember, it's a local maximum. The curve, in fact, I'm sure you're wondering what it looks like. Well, we've found out that it goes through these points, 1, 2, and minus 1, 2. And actually, it looks like this. There's an asymptote here, and then it comes up like that. It's an asymptote here, and it comes up like that. So it's a sort of weird W sort of curve. It can't ever actually be negative. There we go. There's our first example on classifying stationary points. Here's a second question on classifying or finding and classifying turning points. Give this one a go now. Okay, first things first, write it as y is equal to 6x squared minus x cubed, because now it's all with powers and we know how to differentiate this, because that's going to be our next point. Find dy by dx, 12x minus 3x squared. And now set it equal to 0 for the turning points. Okay, what I can actually do is I can divide through by 3, and I'm left with 4x minus x squared equals 0. And I would avoid dividing through by x here, because you just have to think about that solution as well. I've spoken about this. Factorize out the x. X equals 0 or 4. Okay, substitute this back in. When x equals 0, y is equal to, right, we're putting it back into here. Y is going to equal 0. And when x is equal to 4, y is going to equal to 6 times 4 squared minus 4 cubed, which is 6 times 16, that's 96 minus 64, which is 32. Okay, so we've got our other stationary points. Okay, now we need to classify d2y by dx squared is equal to 12 minus 6x. When x equals 0, d2y by dx squared equals 12. So greater than 0, 0, 0, a minimum. When x equals 4, d2y by dx squared equals 12 minus 24, which is minus 12, which is less than 0. So 432 is a maximum. Okay, we've got a cubic here, and what is going on? It's a negative cubic, so it's going to be coming down. This is not going to be an accurate representation, but you can see I've got this minimum and then this maximum. You'll always get that for a cubic. So if you get a positive cubic, I don't think you need to write this down, but it's, it gives you a bit of a feel for the graph. So if you get a positive cubic, you'll get a minimum, you get a max and then a min. If you get a negative cubic, you'll get a min and then a max. Of course, there are counterexamples because x cubed itself doesn't have either of these. So just be cautious. But if there is a max, if there is a stationary point that's a max or a min, that's how it will work. Okay, one more example. Find the nature of the stationary points on this graph. All right, it's already written in a nice form. So the first thing is find dy by dx. It's going to be 3x squared minus 6x plus 3. Set to equal for stationary points. Okay, we've got a quadratic equal to 0. First things first, look for any common factors. There's a common factor of 3, so I can divide through by 3. And I get this quadratic. Okay, this actually factorizes as x minus 1 squared equals 0, so I get a single solution. X equals 1 stationary point, in fact. When x equals 1, y is going to equal 1 minus 3 plus 3. It's also going to equal 1. I found my stationary point. Next, classify d2y by dx squared equals, remember I'm differentiating this thing, 6x minus 6. When x equals 1, d2y by dx squared equals 0. Aha! This is one of those scenarios that we looked at before where we cannot at the moment determine what kind of stationary point it is. Yeah, it's not less than 0, it's not greater than 0, it's equal to 0. What does that mean? Well, what it means is we don't know. We need a different method for how to find out. And this is how we can do it. What we can actually do, and actually I'm going to look at the diagram. I think this is the best thing to do. Okay, for a maximum, yes, we know that d2y by dx squared is less than 0, or or this implies that. But if we look at another method, we see actually dy by dx is equal to 0 at the maximum, but it is positive just to the left and negative just to the right. So actually we can, instead of looking at the second derivative, we can look at the first derivative and check on that, because for a minimum it's 0, but it's negative before and it's positive before. So I'm going to write this down. So we've got 0, we've got positive and negative. That's going to give me a maximum. For a minimum it's negative, 0, positive, the opposite way around. And then we've got the idea of a point of inflection, two different types. Well, here it's going to be positive, then 0, then positive, or the other kind of point of inflection, here we are, negative, 0, and then negative. Remember, I'm talking about the gradients here when I talk about negative and positive. So that allows us to work out, to classify stationary points in a different way, and it really comes into its own when the second derivative is equal to 0. So this is a little summary of what I just said. I'll just give one example again. So for a local maximum, that's going to look like this. Just to the left of the stationary point, this value of x, we're going to get this positive gradient. At the stationary point, we're going to get 0, and just after, it's going to be negative. So let's have a go at doing this for the stationary point we have here. Okay, when x equals, now we need to look just to the left of 1. So we decide how small that is, and I'm going to make it, like, you can make it whatever you like. No, not whatever you like, but make it something sensible. I'm going to look at 0.9. That is just to the left of this value of 1. I could do 0.99, I've just chosen to do 0.9. And I get that dy by dx is equal, okay, I'm putting it back into this thing here, it's going to be 3 times 0.9 squared minus 6 times 0.9 plus 3. And I get 0.03, which is greater than 0. When x is just to the right, 1.1, okay, I can work out dy by dx again. Oh, and I get 0.03 again, greater than 0. So if we put this together, what we've just shown is that the gradient is positive, then it's 0 at the stationary point, then it's positive. So 1, 1 is a point of inflection. It won't always be a point of inflection, but it is in this case. That is an example of how you can use the gradients to classify stationary points, looking to the left and to the right of the stationary point. Finally, let's just check the second method on an example we did earlier. So for the second example, we used the second derivative and we worked out these stationary points. The first one a minimum and the second one a maximum. But let's just check our understanding of that method, because I went through it quite quickly, and see if we can do the same here. So if you're feeling confident, pause the video and give it a go. Otherwise, I'm going to talk about it. Okay, so we've got y. I've given you dy by dx from before, and I've given you the stationary points from before. So let's first of all look at 0, 0, and I'm going to look just to the left. And maybe we should get even closer to 0. But the point is that you know, if you look too far from the stationary point, and maybe you know, if you look over here, then you might get a positive gradient when actually it should have been negative. because you don't know what fine detail there might be. We'll get away with it here, but it is just good practice to look quite close. So I'm going to look a bit closer here. X is equal to minus 0.01. I mean, we're going to use the word imply, like the symbol implies here. Implies dy by dx equals, and then I can work that out, 12 times minus 0.01 minus 3 times minus 0.01 squared. Okay, and I get a negative. If I then look just to the right, I get a positive. So it goes negative, then 0 at the stationary point, and then positive. I've shown that it's going to be a minimum. Okay, it's a little bit more technical. You need a calculator, but you can get there. I hope that makes sense. Let's try the other one. We've got 4 and 32. So let's look at x is equal to 3.99. Okay, and I actually get 0.1197. And then 4.01 just to the right of it. Sorry, 4.01, did I say that? And lo and behold, I get minus 0.1203. So this time it's positive to the left, then 0, then negative, and I got myself a maximum. So that was just the last example, last chance in this lesson for you to sort of develop understanding of this method. So we've covered a lot today. Whew. We've talked about higher derivatives and finding them, where the notation came from. We've shown that we can work out the fourth derivative. We've shown the physical meaning behind some of it. Then we've looked at how the second derivative can be applied to stationary points, revising, finding stationary points along the way. When it's equal to 0, it's a special case and we cannot determine it. We did some examples of different graphs. We saw for one of them, when it's equal to 0, we had to use a new method, which I've then spoken about. You actually look at the gradient to the left and the right. And in this case, we've got a point of inflection. We then looked back at the second example and showed we got a max or a min. Whew, good bit of maths there. I hope you're feeling happy about all of this.